Hey guys, today we're going to be connecting the ideas of potential energy and kinetic energy in a graph that is known as a heating curve. So let's go ahead and start by taking a look at this heating curve idea and what each part of the curve represents. So the first thing we're going to do is we're going to go ahead and draw the curve. And as with any graph, the first thing we need to look at is the axes in the graph and figure out what their units are and what they're representing. So as you can see in this graph, we have temperature on the y-axis and energy added on the x-axis. Now what this suggests is that we go from left to right on the graph, that we're adding more energy into the system, and some of it would be represented by a change in temperature. So let's start by drawing the relative shape, and then we'll discuss what each part of the shape represents. Okay. Each of these different segments represents a different process. Now, I'm going to go ahead and start by labeling each part. So when I label these, this first region, where you can see the slope line, represents my system in solid form. This represents my system in liquid form. And this represents my system in gaseous form. That means that within these three regions, we have a system with a single phase present. Within these regions, that's a phase change. So this region represents the phase change between solid and liquid. This we know as fusion or melting. And this region represents the change between a liquid and a gas, also known as vaporization or condensation. So now what we represent are each different zone of our graph. Next, we're going to talk about what each means. Now, within our solid, liquid, and gas regions, you can see that the temperature is changing. As we add energy, when the temperature changes, that means we're changing kinetic energy. Because we're changing kinetic energy, you have to remember back to what causes a change in kinetic energy of any substance, and that's its specific heat. So the relative change in temperature is determined by the specific heat of that substance. So when we look at these three different regions, all of which have slopes, we can see that the change in temperature as the energy is added is going to be dictated by an equation, Q equals mc delta T, where Q represents the amount of energy added, C represents the specific heat of the substance, whether it's solid, liquid, or gas. And by the way, in each of those three zones, it could be different. Solid water has a different specific heat than liquid water and has a different specific heat than gaseous water. So again, each of these three represents a different substance in terms of its phase and thereby a different specific heat. So each of those sloping areas represents a change in kinetic energy. A change in potential energy is represented by the horizontal lines. The reason is because we are adding energy, and yet it's not going into the temperature. Temperature, remember, is a measure of average kinetic energy. So if the kinetic energy is not changing, it must be the potential energy. So when we look at this and this, what we're seeing here is a delta H. So this would represent delta H of fusion, and this would represent delta H of vaporization. All right, and remember, delta H is joules or kilojoules per mole, or Q divided by moles. So when we look at these three different parts, solid, liquid, and gas, each represented by a Q equals mc delta T equation. And when we look at these two horizontal parts, we see that they are represented by a delta H equation. Here, the delta H of fusion, and here the delta H of vaporization. Next, we're going to talk about what. Now let's talk some numbers. When we look at these three sloping regions, what we realize if we do the quick analysis is the slope is representative of how much energy is added compared to its change in temperature. Well, if we look at my equation, Q equals mc delta T, if we have a lower amount of heat added and yet a greater temperature change, that means my C, my specific heat capacity, must be lower. So a more rapid temperature change or a steeper slope in these three regions represents a smaller specific heat of that substance. Each of the horizontal components, being represented by my delta H, is going to be representative of a phase change. Now, a phase change in this case is energy added to separate intermolecular or interparticle forces. And what we realize is the longer that zone, the more energy must be added to complete that phase change. That means that the longer this is, the greater the delta H value is going to be. Additionally, be aware, horizontal, no change in temperature. Any energy added is going into a situation where we're changing only the potential energy. Therefore, these zones are at what we call a thermal equilibrium. Thermal equilibrium, no temperature change. So even though the temperature is not changing, energy is being used just for a different process, all right? Not heating it up, but instead changing the phase of our substance. During these zones, both the solid and the liquid, or the liquid and the gas, exist in an equilibrium situation. One of the last pieces of information we can garner from this heating curve is going to be boiling point and melting point information. All we have to do in that situation is look at our point where we are transitioning from solid to liquid and find the temperature at which that happens. That's our melting point. Find the point where a liquid transitions to a gas, find the temperature, that's our boiling point. So we can find a lot of information just by looking at this one curve. If we connect back to our mc delta T and our delta H equations, we can quantitatively assess the amount of energy being input compared to where we are on this curve and actually be able to use this to perform some calculations. Now, beyond just a heating curve, you might also see a cooling curve. A cooling curve takes a heating curve and simply flips it. And instead of adding energy, we're now removing energy. So as you can see, we start here as a gas. We transition through the condensation process into a liquid. Liquid then converts into a solid through the freezing process, and now we're in a solid. The general components of each, the heating curve and the cooling curve, are the same. Okay? But be aware that you can see it in both directions. You just need to make sure you're correct about assigning which phase at which point. The other thing is these are idealized graphs. This might not be what you really see. In reality, what can sometimes happen is as you're about to transition from one phase into the other, we have a moment of supercooling. What this is it's a change in temperature that might actually drop you slightly below or raise you slightly above the temperature of the phase change, where that energy is then going to be utilized in the phase change. The way that looks on some of these graphs is going to be like this, where you just slightly overshoot the temperature at which you're going to have the phase change. This shouldn't affect anything in terms of your analysis, though. You're still going to be at the same temperature beginning your phase change, but some molecules, due to the nature of temperature, which is the average kinetic energy, some molecules are actually going to dip below before transitioning phase. This is a normal occurrence. This is an idealized situation, but be aware that it can happen. So when you see this, don't worry. It still represents the point at which a phase change is going to occur, but we're now just having to think about a real-world situation as opposed to an idealized situation. All right, now that we've gone over this curve, let's give you a chance to go ahead and label some of it yourself. So I have these 4 questions that I want you to look at and label each part of the curve respectively. All right, so here we go. First, I want you to tell me where along this curve, between any points, is it going to be in its solid phase? Secondly, where is the melting process occurring between points? vaporization. So at what points is vaporization occurring? And where is my delta H magnitude going to be greater? Would it be the delta H of fusion or the delta H of vaporization? So take a few seconds to label your curve. All right. When you're done, go ahead and unpause the video. Come back and we'll go ahead and go through it together. All right, so now I've had a few seconds to work on it. Let's go ahead and go through this together. The first one was asking, where am I in my solid phase? Now my solid phase, if you remember from the heating curve, is going to be the point where I have the lowest temperature. It's going to be a change in kinetic energy because we're staying in the same phase. And so therefore that's going to be A to B. So from points A to B, I'm in my solid phase. The second question is, where's my melting process occurring? Well, if from A to B represents a solid, then a change of potential energy away from a solid would be a change of potential energy from solid to liquid. This would be my fusion process, or in the direction we're going, the melting process. Finally, here we got two more. Vaporization. Where's vaporization occurring? That's between D and E. So this is going to be the process by which I go from a liquid into a gas, and that process is, again, my delta H of vaporization, or my heat of vaporization. Finally, which one in magnitude is greater, the delta H of fusion or the delta H of vaporization? Remember that the length of the lines of our phase changes represents how much energy had to have been added in order to go from one to the other. Notice from B to C, we've had to add that amount of energy. From D to E, we've had to add substantially more. So from that point to that point is longer than from that point to that point. Therefore, my delta H of vaporization is of a greater magnitude than my delta H of fusion. And this is not abnormal. We normally see a greater delta H of vaporization than we do a delta H of fusion. And the reason for this is because to go from a solid to a liquid, you're not really separating the molecules or the particles. They're still pretty together, right? Remember, a liquid is not compressible. A solid is not compressible. In order to transition to a gas, however, we have to rip all the molecules apart. That takes more energy. Okay, so all the molecules are going to be separated out into their gaseous phase, and that's going to require more energy. So normally, the way we see a heating curve look is that my delta H of fusion is going to be less in magnitude than my delta H of vaporization. All right, so that wraps up today's video. Let's do a quick recap. Today we started by introducing what is a heating curve, what does it look like, and also what do both the horizontal and sloped parts of the curve represent. Remember, horizontal lines represent a change in potential energy. Those are your phase changes. And then your sloping lines represent a change in kinetic energy because it's a change in temperature. All right? Remember, the length of the line and the slope of the line matter. So the longer a horizontal line is, the greater the enthalpy of that phase change is, and the more steep the slope is, the less energy is required to change the temperature, thereby the lower the specific heat of that substance is. I'd like to thank Tyler Rodig and Jackson Kosavera for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.